Working. As said before, capacitor consists of two conductors separated by a dielectric. When there is any potential difference between the two conductors, electric potential is developed. This causes the capacitor to charge and discharge. Let us understand this in a practical way. When the capacitor is connected to a battery, a DC source, current starts flowing through the circuit. Thus negative charge is accumulated on one plate and positive charge is accumulated on the other plate. This process continues until the capacitor voltage reaches supply voltage. When the charging voltage is equal to the supply voltage, capacitor stops charging further even though the battery is connected. When the battery is removed, two plates will be accumulated with positive and negative charges. Thus the charge is stored in the capacitor. But when the supply voltage is from an AC source, it charges and discharges continuously. The rate of charging and discharging depends on the frequency of the source. Example. Working can be understood using simple example here. Below circuit shows two switches A and B. When switch 1 is closed, current starts flowing from the battery to the capacitor. When the capacitor voltage reaches the supply voltage, it stops charging further. Now connect the switch to position B. Now you can observe the LED starts glowing and this slowly fades out as the capacitor is discharging. Capacitance of the capacitor is given by C equals K/D, or C equals epsilon A/4 pi D, or C equals epsilon O asterisk epsilon R, A/D, where C, capacitance of the capacitor, A, area between the plates, D, distance between the two plates, epsilon O, permittivity of free space, epsilon R, relative permittivity, K, dielectric constant. Capacitance of a capacitor. Capacitance is the property of the capacitor that defines the maximum amount of electrical charge stored in it. It exists in nature everywhere. Capacitance may vary depending on the shape of the capacitor. Capacitance can be calculated by using the geometry of the conductors and dielectric material properties. Let us see the capacitance of a parallel plate capacitor. Capacitance is defined as the ratio of charge, Q, on the either plates to the potential difference, V, between them. C equals Q/V. Thus current can be obtained as I, T, equals CD, V/D, T. This can be expressed farads, F, which is named after English physicist Michael Faraday. From the above definition we can observe that capacitance is directly proportional to the charge, Q, and is inversely proportional to the voltage, V. Capacitance of the capacitor can be increased by increasing the number of plates, which helps to maintain the same size of the capacitor. Here, area of the plates is increased. Standard units of capacitance. Generally farads is a high value, so capacitance is expressed as subunits of capacitor real time such as microfarads, UF, nanofarads, NF, and picofarads, PF. Most of the electrical and electronic applications are covered by the following standard unit, SI, prefixes for easy calculations. Voltage rating of a capacitor. This is not voltage until which the capacitor charges but the maximum voltage until which the capacitor can operate safely. This voltage is called as working voltage, WV, or DC working voltage, DCWV. Below figure shows the voltage rating of the capacitor. If the capacitor is applied with voltage greater than this voltage, it may be damaged by producing an arc between the plates due to dielectric breakdown. While designing the circuits with capacitors, care should be taken such that the voltage rating of the capacitor is greater than the voltage used in the circuit. For example, if the circuit operating voltage is 12 V, then it is necessary to choose a capacitor with voltage rating of 12 V or above. This working voltage of a capacitor depends on the factors like dielectric material used between the capacitor plates, dielectric thickness, and also on the type of circuit which is used.